So what can we say about equilibria from what we know so far? Equilibrium. Equilibrium is something that has a property that X, equilibrium Q, let's give it a name. We usually label solutions by some kind of label. So Q has a property that when I look at evolution time t of Q, it just stays where I am for all times. So it looks like there's nothing interesting, but however, if I look at the neighborhood of Q, something will happen because neighboring trajectory, even though I'm not moving, they have non-zero velocity fields because, generically, I should say the equilibria are isolated unless there is a symmetry principle that forces them to be in families. But usually, you have some general function, you're computing zero of it, that's the map forward in time, minus initial point, and generically, they tend to be isolated zeros. So when I look at the neighborhood, the law is very simple. We already did this because if I look at the difference of x minus the initial point xq, so I look at this as a function of time. At time 0, I have a thing. And now, because this is equilibrium, the matrix, which is a gradient of the velocity field, because I am evaluated at this point, A is also just function of the point and constant out of it's constant. Do you agree with me? The matrix of velocity, okay. But we already did the actual thing for constant matrices. So we know that this grows like E to this constant matrix AQ. I'll just label it because it's a constant matrix. And it's exponential and it changes with time. So, the Jacobian is known the moment I know the matrix because there's nothing about time ordering. It's all simple. It says it has very simple dynamics. The neighboring points are just being pushed out or squeezed or rotated exponentially by this matrix. And you can see that the time t is bogus because the only thing you really should know is the eigenvalues of that object. And that's why in quantum mechanics, this is called Hamiltonian operator. That's why I compute eigenvalues of the Hamiltonian, and that tells you what happens to the vector in time. So Hamiltonian is an exponent, and in quantum mechanics, this object here is called unitary evolution operator. But it's e to the integrated Hamiltonian.